Hello everyone, this is Wilson Fandino. I'm one of the senior TAs for this PPCR course, and I would like to talk to you about sample size calculation today. And then my presentation today is going to be focused mainly on sample size calculation for means and proportions. And the reason for this is because the topic is sample size calculation is complex. It's a huge topic because whenever we talk about calculation of sample size, we need to think about the study design. So we have sample size calculation for survival analysis, we have sample size calculation for surveys, we have sample size calculation for cluster randomized trials, and so on. So this is a huge topic, but today I would like to talk about sample size calculation just for means and proportions. Because we are going to talk about calculation of our sample size, so I think it's good to start with the actual equation. The idea is not to memorize the equations whatsoever, but at least to understand what is this all about. And I would like to start my presentation by talking about the Z-score, because I think this is a very important topic, a very key concept in statistics. In the simplest version of the Z-score, I would say that this is just the standardized way. It's a standardized way to present the data. What I mean by that is that you may have heard that the Z-score is just the subtraction of the value of any observation minus the mean of that value divided by the standard deviation of the sample. This is a slightly different definition of the Z-score, because here I'm saying that the Z-score may be defined as the subtraction between the sample, the study sample mean, right, which is represented here by X bar, minus the true population mean, which is represented here by mu, divided by the standard error of the mean. So the standard error of the mean is nothing else than the standard deviation of the population, and is defined by the standard deviation of the sample divided by the square root of the sample, the actual sample size of our study. So this is a good estimation of the true population standard deviation. So here we have four key components for the Z-score, which are the mean for the sample, which is X bar, the true population mean, the standard deviation of the sample, and the actual sample size of the study, right? Now, so if we want to translate this concept into the context of sample size calculation, we will need to divide this Z-score into two types, shall we say, types of Z-score, which are the Z-score for alpha and the Z-score for beta. And I will explain to you later on what I mean by this, but it's good to get used to this, because you will see this everywhere whenever you are reading about the sample size. So this is, in this case, is the Z-score for 1 minus alpha over 2 plus the Z-score of 1 minus beta, which is equal to in this setting, it will be the subtraction between the mean for the group X minus the mean for the group Y. So imagine that you are conducting a randomized clinical trial, so you have randomize patients to group X and group Y. So this is what I mean by this. And this is going to be your effect size. So this is the mean difference between the two groups, right? So the expected mean difference of these two groups is what we know as the effect size, right? And then you have to divide this by something slightly more complex than this equation for the for the standard error of the population, standard deviation of the population, which is the standard error. And this equation is given by the standard deviation of the group X divided by the number of observations on that group, plus the standard deviation for the group Y, and divided by the number of observations for that group too, right? So what I wanted to show you here is that the intuition behind the calculation of the sample size is coming from the Z-score. So you can see here that the structure is very similar, but all I'm doing here is just to make a decomposition of the Z-score into Z for alpha and Z for beta. And this is my effect size, this is my sample size calculation, sorry, my standard deviation, and this is the actual sample size, right, for each group. If you do a little bit of rearrangement, so you will come with this formula here, which means that for each group you will need 2 times the square root of the standard deviation times something a little bit complex at first, but like I said, I'm going to explain to you what I mean by this, but it's just the square of the sum of the z's for alpha plus the z for beta, right? And all this divided by the square of the effect size, right? So all I'm doing here is just replacing this x bar minus y bar by d, this d here, and then in the end you will come with this equation, which is a very basic equation for the calculation of sample size. So once you understand where is this coming from, so you will realize that many equations are having the same structure. So here in this slide, I'm showing you the equations for each study according to the type of design. So you have here the superiority design, the equivalence design, and the non-inferiority design. So you will see that they are very similar. I would like to focus today on the superiority trials, right? But the purpose of this slide is that all these equations are really similar each other, right? So in terms of the comparison of means for a superiority trial, so you will see here that you will need 4 times the square of the standard deviation of the sample, and again this is the same formula that I introduced you in the last slide. But I wanted to show you that it's very similar to the comparison between proportions. So you can look at this. So the components of the z of 1 minus alpha over 2 plus z of 1 minus beta, and this term square is exactly here, this term, and same for the effect size, right? So the only difference between the means and proportions in terms of sample size calculation is the estimation of the standard deviation, which in this case is given, in the case of proportions, is given by the proportion for group 1 or of the group X times 1 minus that proportion plus the proportion of the group Y times 1 minus that quantity, right? So basically it's very similar, and the concept is really similar when you compare the means and proportions. And then when you are calculating proportions, especially if you are calculating with this data or with any statistical software, so you will see that the actual calculation is slightly different from this equation. And the reason for this is because the software is applying something that is called continuity correction. So this is nothing else that acknowledging the fact that the calculation of the sample size is coming from an approximation for the normal distribution. And then because it's an approximation, we need to multiply this by correction factor, which in the case of proportion is given by this equation here. And again, I'm representing here the proportion for X and minus the proportion for Y, and this is the sample size, right? For per group, as I'm showing you here. So what I mean by continuity correction is that whenever you are calculating the sample size for proportion, you are doing something like this, right? Where every scale is given by certain proportion, but then you have to approximate this to the normal distribution, and this, by the way, is representing the effect size of the two groups. So imagine that this is the this is the first group that we are comparing, and this is the second group, and this is the distance between those means is just the effect size, right? So what we are doing with the continuity correction is to make this curve nice and smooth as this one, in order to, like I said, to acknowledge the fact that we are using an approximation to the normal distribution. And because we are not talking about the continuous variable, we are talking about the proportion, which is not a continuous variable. So we need to apply this continuity correction in order to make these curves nice and smooth. So I already introduced you into the concept of Z-score, which I believe is very important in the context of sample size calculation. So basically, what you are doing with the Z-score is just to calculate the area under the curve for this normal distribution, right? So imagine that this is the standardized normal distribution, where we have a mean of 0 and standard deviation of 1. And so this is exactly what I'm representing here. And then imagine that you have to calculate the area under the curve. So the area under the curve for the when the standard deviation is 0 is exactly the middle. So that would be the 50%, right? And then in that particular case, the Z-score, which is nothing else than the standardized value of that observation, is just 0, right? So when the Z-score is 0, the area under the curve, which is represented by this area, is exactly 50%, right? Now, if you want to calculate the area under the curve, or of the Z-score of 0.84, so that would be exactly 80%, which is 0.8 here. So that means that if I wanted to calculate the area under the curve, or this red plus this blue area plus this pink area plus this purple area, So you will have exactly 80%, which is represented here by the area under the curve. Something similar happens when you want to calculate the area under the curve for the 95%. So in this case, the z-score would be 1.64, and that means that the observation is 1.64 times away from the mean, right? And finally, you wanted to calculate the 97.5% of the area under the curve, which is all this area, the green plus the yellow plus the red plus the blue plus the pink plus the purple area. So that corresponds exactly to 1.96. And I hope this is familiar to you, because the 1.96 is a very important number in statistics, because we use this for the calculation of confidence interval, and also for the calculation of sample size, right? So this is all about the calculation of the area under the curve. So this is what I wanted to represent here. So once you understand this, so hopefully you can interpret the Z-table, which you can find in any statistical book or on the internet. Of course, you don't have to memorize this whatsoever, and you don't really need to use this in your daily practice, because this data will do everything for you. But I think it's good to know where all these things are coming from. So what you can see here is the actual Z-score, right? So the Z-score is coming, it's beginning from 0 here, in my example, to 3.9, right? So like I said, a Z-score of 0.0, which is exactly this corner, corresponds to an area under the curve of 50%, okay? Now, if I wanted to know, like I said in my earlier slide, what the area under the curve is for 1.96, which is here, so all you need to do is just to allocate here the 1.9, which is in this case here, and then the column that corresponds to 0.06, and that intersection with the row of 1.9 comes to the area under the curve of 1.96, right? So what I mean by this is that the area under the curve for 1.90 is exactly 0.97128, right? And then if you move on, the area under the curve for 1.96, which is here, is exactly 0.975, which is exactly this quantity that I gave you here, right? So these are the Z-scores, and then this is yet another representation of the same situation, where you have the area under the curve and you have the Z-score. I've just said that 1.96, the Z-score of 1.96 corresponds to an area under the curve of 0.975. And then I think it's good to kind of get used to these numbers, especially for these cutoffs, because we have here for an area under the curve of 80%, you have a Z-score of 0.8416. For 90%, you will have 1.28, which corresponds here to this intercept, right? And then for 95%, you have 1.645. For 97.5%, you have 1.96, and so on. But these numbers, we will need to use these numbers in order to calculate the actual sample size. And this is what I meant in the beginning of my presentation by the Z-score for alpha and beta, right? So very often in terms of the z score for alpha, so we choose the alpha or 5%. So let me just show you again this. So I say that the sample size is given by the standard deviation, which is the first component, the z-score for 1 minus alpha over 2, plus the z-score for 1 minus beta. So because the alpha is usually 5%, so that means that the z-score for 1 minus 5% over 2, it comes to 0.975, right? So the z-score for 0.975 is exactly 1.96 here, right? It's 1.96. And then on the other hand, you have to choose a z-score for a given beta value, and the beta value is just the complement of the statistical power, right? So let me explain to you this better. If you say that your study is going to have 80% of power, so that means that your beta value is going to be 0.2, because 1 minus 0.2 is 0.8, which is 80% of the desired power, right? And then on the other hand, if you want to, you want a beta value of 0.8, sorry, 0.2 in this case, or a statistical power or 0.8, so you will need this number, right? This number here, which is 0.8, okay? So you will need this 0.8416. On the other hand, if you want to increase your power to 90%, which is here, the area under the curve is 90%, so you will need to use, instead of 0.8416, 1.2812 in that case, right? And and then the same happens with the alpha value, because we already say that the alpha over 2, 1 minus alpha over 2 is 0.9075, and in that case the z-score is going to be 1.96. But if you wanted to increase or decrease the alpha value, so you will need to use these numbers or these numbers instead, right? Like I said, we usually go for an alpha critical value of 5%, so we very rarely change this, but what we usually change is the statistical power, which is given by these z-scores, right? So that means that if you wanted to conduct a clinical trial with 5% of alpha critical value and with 80% of statistical power, which means 20% of beta value, 0.2 beta value. So you will need the z-score for 1 minus alpha over 2, which is exactly 1.96, plus the z-score for 1 minus beta, which is exactly 0.8416, right? So you need to add the 1.96 plus 0.8416 and then square this, and then once you get this number, you need to multiply by the square of the standard deviation, and then multiply by 2, and then divide this by the square of the effect size, right? So this is what we mean by z-score by for 1 minus alpha over 2 and z-score for 1 minus beta. So hopefully you realize that in order to calculate the sample size, we have four very important components, four key components. So the first one is given by the effect size, right? And the effect size, again, the effect size is here. In this case, is represented by D. And then you will have the standard deviation for one sample, and then the standard deviation for the other sample. In many cases, we assume that the standard deviation is equal among samples, but this is not always true. So we also have variations of the equation for different standard deviations of the groups. But let's assume that the standard deviation is the same for the group X and the group Y, right here. So all we wanted to do is just to compare this population with this population, and we are just trying to estimate the required sample size for this study, right? So we have effect size, we have standard deviation, and then the third component is the alpha value, which I already talked to you about. And then the fourth component is the beta value, and we say that the 1 minus the beta value is nothing less than the statistical power, right? So I think it's good to keep in mind this figure, because you will need this in order to figure out what happens when you increase the alpha value or you decrease the alpha value, what happens with the statistical power. Because if you wanted to increase the alpha value, so that means that this line here is going to be here, like more or less here. I will show you in my next slide. So that means that the statistical power is going to be increased. But if you wanted to decrease the alpha value, so the line would be here, right? So that means that your statistical power is going to be decreased. So in this figure, the statistical power is given by the area and the curve represented in red, right? And the alpha value is represented by the area in yellow, which is here. And the beta, which is 1 minus the statistical power, is represented by this green area here, right? And the confidence interval is represented here in blue, right? Because most of the times we are testing a two-side or two-tailed hypothesis, so we need to take into account this alpha value of this tail, not only this one, but also this one. And this is the reason in the formula I introduced you before, I say that the alpha is divided by 2. So all I'm saying here is that I'm testing a two-tailed hypothesis, and I not only care about the this tail of the hypothesis, which is given here in this yellow area, but also this area is important for the sample size calculation, right? So now let's think about what happens when we wanted to increase the statistical power. So if you wanted to increase the statistical power for this study without increasing the sample size, obviously, because you want to increase the statistical power without modifying your alpha critical value, all you need to do is just to increase the sample size. But if you wanted to increase your statistical power with the same sample size without modifying the sample size, so you need to sacrifice a little bit of alpha value, right? So this is what I'm representing here. So here the area under the curve is is much more than my early slide here, right? But this is at the cost of increasing the alpha critical value. In this case, I have increased the alpha critical value to 10%, right? Because in that case, the confidence interval is going to be 90%. So by the way, here, this is represented, this blue area is represented 95% confidence interval, and this area is 2.5%, and this area is 2.5% of the area under the curve. So that comes to 100%, right? And in this case, if you wanted to increase the statistical power again without increasing the sample size, so you will need to increase, sacrifice a little bit the alpha value. In this case, this yellow area is represented by 5% of the area under the curve, and this is the other 5%, and the remaining 90% is just the confidence interval, right? So now you understand what I mean by statistical power. You understand what I mean by beta value, which is this green area. You understand what I mean by alpha critical value, which is this yellow area plus this yellow area. And you will understand what we mean by confidence interval, which is exactly the remaining of the area under the curve for this, right? And then what happens if you wanted to test a one-tail hypothesis? So all you need to do is just remove this area under the curve that I was representing here. And in this case, it's 95% confidence interval, and this area under the curve will be the remaining 5% of the area under the curve, which is the alpha critical value for one-tail hypothesis, right? So something similar happens with the effect size because, and again, this is in the hypothetical case that you are not increasing your sample size. So if you are not increasing your sample size and you wanted to modify your effect size, this is what happens in terms of the statistical power. So so imagine that this is the effect size that you are expected, that you are expecting here, right, between this population and this population. So for a given alpha critical value here, right, so the statistical power is going to be given by this area under the curve, which in this case is represented in yellow. Now, if you wanted to decrease the effect size in order to calculate your sample size, so what happens with your statistical power is that it's going to be decreased significantly, right? As you can see here. Right? So this is why people tend to overestimate the effect size in order to have a decent statistical power beforehand, which is actually a bad practice because the effect size it is what it is. But because the alpha and the beta values are very difficult to change in many situations, so what some researchers do is just to manipulate the effect size in order to have a good statistical power. But the problem with this is that once the study is done, if this effect size was not the true effect size observed in your sample, so you will have something like this, right? So imagine that before starting you were expecting an effect size as large as this, but then after finishing your study, you realize that your effect size was not as big as you were expecting. So initially in your protocol, you were planning to have 80% of statistical power, but because the actual effect size was so little, the statistical power is going to be really decrease here, like something like 40% or even less than that, right? So you will have very serious issues with the statistical power if you are not honest with the specification of the effect size in your equation, right? And this is what will happen if you actually increase the sample size and you wanted to keep the same effect size here. So you just need to increase the sample size in order to keep the same statistical power. And you have to look here the different values on the x-axis in order to understand what is going on here. And obviously, if you increase this standard deviation, so you will need less and less sample size. Obviously, because the more you increase the sample size, the more accurate your estimation of the mean is. So the easier is going to be to detect a difference between means, right? So what I'm trying to say here is that for such a large standard deviation here, it's going to be very difficult to demonstrate a difference between this mean and this mean, right? But then if you increase the sample size, you are going to decrease the standard deviation here. So it's going to be relatively easier to demonstrate a difference between this mean and this mean. And if you further increase your sample size, so your standard deviation is going to be even less than this. So it's going to be even easier to demonstrate a difference between these two means. So I think it's clear that demonstrating a difference between these two groups is much more difficult than demonstrating difference between these two, even though the effect size is exactly the same. All I'm doing here is just to increase the sample size. And by increasing the sample size, I'm decreasing the standard deviation, and I'm facilitating a potential difference between means, right? And this is just to show you what happens with the power and the sample size, what happens with the power and the effect size, and power and the significance level, which is the alpha critical value, and the power and the standard deviation, right? So the more you increase the sample size, the power is going to increase unavoidably, right? The more you increase the effect size, the power is going to increase as well, right? The more you increase the alpha critical value, your power is going to increase as well. But the more you increase the standard deviation, your power is going to be decreased in this case. Something similar is happening here. I'm just comparing the power with the effect size in this case, and then I'm just increasing the sample size from 50 to 100 to 200 and 300. So the more you increase the sample size, so you will see what happens here with the power, right? And then in this case, the X value is the standardized effect size, right? This is something similar as well. So here I'm comparing the total sample size, in this case with the power, the total sample size with the effect size, the sample size with the alpha critical value, and the standard deviation. So it's something similar that what I showed you a couple of slides before. And then something that I wanted to show you as well is that we do have specific considerations for the sample size calculation. I think I mentioned before that the equation that I given to you is assuming that the standard deviation is roughly the same between the two groups, but we also have different equation whenever the standard deviations are considered unequal. So you just need to sum up the standard deviation for group X and group Y. We also have a different well, it's not that different, but it's just a correction factor for unequal group sizes. So when the group sizes are unequal between the two groups, so you just need to multiply the calculated sample size with the standard equation by this factor, which is given by 1 plus r squared over 4 times r, where r is the ratio of the group sizes, right? So usually in clinical trials you will have 1:1 ratio, but sometimes you will have 1:2 ratio or 1:3 ratio. So in this case, in the case of 1:2 ratio, so the r value is going to be 2. So 1 plus 2 is equal to 3. 3 squared is equal to 9. And this 9 is going to be divided by 8, which is 4 times 2 here in this particular case, right? We also have corrections for the expected rate of withdrawal of the of dropout of the patients. So if you are expecting a significant amount of patients who are going to drop out, you have here a correction for this formula, which is given by your estimated sample size divided by 1 minus the proportion that you are expecting to drop out in that case. Something similar happens with the non-adherence, which is a similar concept but not exactly the same as the withdrawal. So again, we just need to adjust this calculated sample size by dividing the estimated sample size by the square of 1 minus the proportion for the treatment minus the proportion of the control group. What I mean by proportion is the proportion of non-adherence in that case. So this is all I wanted to show you today. I hope you learned something new today, and I'm very happy to take any questions or on my email address, which is wilson.fandino@ppcr.org. Thank you very much for listening, and see you next time.